sklearn, linear model, logistic regression. Description. A logistic regression model is a statistical method used for binary classification problems. It predicts the probability of an instance belonging to a specific class 0 or 1 based on the input features. The model uses a sigmoid function to map the linear combination of features to a probability between 0 and 1. Inputs. X, a 2D array-like structure representing the features independent variables of the training data. Each row corresponds to an instance, and each column represents a feature. Y, a 1D array-like structure representing the target variable dependent variable of the training data. It should contain the corresponding class labels 0 or 1 for each instance in X. Outputs. Self returns the fitted logistic regression object itself. This object can then be used for making predictions on new data. Core, a 2D array representing the coefficients of the linear model. Each row corresponds to a feature, and the values represent the weight associated with that feature. Intercept, a 1D array representing the intercept of the linear model. Steps. Initialize the logistic regression model with desired hyperparameters, e.g., regularization strength. Solver. Fit the model to the training data X, Y by calling the fit method. This step involves finding the optimal coefficients weights that minimize the loss function, e.g., log loss. Use the fitted model to make predictions on new data by calling the predict method. This method predicts the class labels 0 or 1 for each instance in the new data. Metrics. Accuracy, the proportion of correctly classified instances. Precision, the proportion of true positive predictions out of all positive predictions. Recall, the proportion of true positive predictions out of all actual positive instances. F1 score, the harmonic mean of precision and recall. AUC area under the ROC curve, a measure of the model's ability to distinguish between classes. Visualization plots. ROC curve plots the true positive rate against the false positive rate at various thresholds, providing insight into the model's performance. Precision recall curve plots the precision against the recall at various thresholds, highlighting the trade-off between these metrics. Fine-tune parameters. Penalty, the type of regularization to apply, e.g., L1, L2, elastic net, none. Regularization helps prevent overfitting by penalizing large coefficients. See the inverse of the regularization strength. A lower value of C corresponds to stronger regularization. Solver, the optimization algorithm used to find the coefficients, e.g., liblinear, Newton CG, LBFGS, SAG, Saga. The choice of solver can affect the speed and accuracy of the model. Maxiter, the maximum number of iterations for the solver to run. Toll, the tolerance for the optimization algorithm to stop. Uncertainty methods. Confidence intervals can be calculated for the predicted probabilities using techniques like bootstrapping or Bayesian inference. Prediction intervals can be constructed to provide a range of possible outcomes for predictions. Challenges and fixes. Challenge 1: overfitting. The model may perform well on the training data but poorly on unseen data. Sample use case that resulted in challenge 1: training a logistic regression model on a small dataset with many features may lead to overfitting, where the model learns the training data too well and fails to generalize to new data. Fixes to challenge 1. Regularization: use L1 or L2 regularization to penalize large coefficients and prevent overfitting. Feature selection: remove irrelevant or redundant features to reduce the model's complexity and improve generalization. Cross-validation: use techniques like k-fold cross-validation to evaluate the model's performance. on unseen data during training and select the best hyperparameters. Challenge 2, data imbalance when one class is significantly more prevalent than the other. The model may favor the majority class and perform poorly on the minority class. Sample use case that resulted in challenge 2, training a logistic regression model to detect fraud. Where fraudulent transactions are rare compared to legitimate transactions, may result in the model being biased towards predicting legitimate transactions. Fixes to challenge 2. Oversampling, increase the number of instances of the minority class by replicating them or generating synthetic instances. Undersampling, reduce the number of instances of the majority class by randomly removing instances. Class weighing, assign different weights to the classes during training to give more importance to the minority class. Use specialized algorithms. Consider using algorithms designed for imbalanced datasets, such as smooth synthetic minority oversampling technique or cost-sensitive learning.